Okay, so we've learned about radiation and the black body, and we know that black bodies aren't, they're perfect, and we know that nothing in the universe is perfect. And so we're going to talk about specifically um, the Earth being seen as something close to a black body, but not exactly a black body. Okay, and because because the Earth isn't a total black body, we have what's called an atmosphere, and our atmosphere causes what we call the greenhouse effect. Okay. And so we are going to learn today. I will explain how greenhouse gases absorb infrared radiation using emissivity, albedo, and the solar constant. Okay, so we talked about black bodies and the fact that most objects do not function 100% as a black body. So because they're not a black body, we're now going to call them a gray body. Okay. A gray body emits less energy per second than a black body of the same dimensions and temperature. Okay. So there's a relationship between these where the ratio of the energy emitted can be found. And so that ratio, which is the decrease in energy that's used by the black body, um, is called the emissivity. Okay, emissivity. The emissivity is the power emitted by the real object, okay, the gray body, divided by the power emitted by the black body. And make sure that, when you're looking at these, they have to be of the same size and the same temperature, right? The same area and the same temperature if we're going to look at them. So thinking about emissivity and the fact that because it's a ratio, it has no units, the emissivity of a black body would be 1, right? Because the power emitted by the radiating object would be exactly the same as the black body, which would give you a number over itself, which is always 1. Okay. An object that completely reflects the radiation without absorbing any of it would be a 0. Um, you know, again, there's no perfect 0, but if you think of like a disco ball or something like that, where it's reflecting everything, right? So the power emitted by the radiating object would be 0, therefore the emissivity would be 0. All right. We can think of gray bodies in the same way we think about black bodies. So Stefan Boltzmann's law still applies. The only difference is that we have to um, figure in that emissivity, that change in energy, right? So we have, in this case, we have the power is going to be equal to that emissivity, right? That ratio times the area times the constant times t to the 4th. Remember, they both have the same area and they both have the same temperature. So that emissivity is really the only thing that's changing. All right. So let's talk about the sun and the earth, right? So because of nuclear fusion, the sun emits large amounts of energy every second. So fusion puts off a lot of energy, and that energy is emitted from the sun in huge amounts every second. But if we think about it, it's emitting that radiation at 90 degrees. And because the earth is small compared to the sun, right? All of that radiation is not going to actually hit the earth. Okay? And so when we look at it, we find that the intensity of the radiation that arrives at the top of the atmosphere, we call that the solar constant. So the radiation goes through the vacuum of space, so it doesn't hit anything, it doesn't decrease, it doesn't increase. So at the Earth's surface, a certain amount of that solar energy contacts Earth's atmosphere. Okay, so that's way up in the sky. Okay, we know that the sun emits 3.8 times 10 to the 26 joules every second. And we know that the sun is 1.5 times 10 to the 11th meters away. Okay, so if we assume that the sun is a perfect sphere, which is that would give it a radius, or I'm sorry, an area of 4 pi r squared. And we look at our intensity, right, which is our power per square meter, right? So power divided by the area. So if we take this power and divide it by this area, we end up with approximately 1,400 watts per meter squared. Now, that's using only two significant figures, and we can definitely measure much better than that. So if we use more precise data, the actual solar constant is 1,360 watts per meter squared. Okay, now that is only hitting Earth's atmosphere. Okay, if we look at the intensity that actually arrives to the Earth, right, Earth's surface, there's 340 watts per meter squared. Okay, so some of it is lost to scattering or reflection back into space. So a part of that radiation is lost before it even gets to the Earth. Okay, this intensity then continues to the Earth's surface, where, since it is not a black body, it is both absorbed and scattered back toward the atmosphere. Right, so here's our 340 watts per meter squared, and it's going to keep going. When it gets to the Earth, it's going to be absorbed by the ocean, the land, the polar caps, wherever it is that it's landing. All right, but there are a few things that scatter it back up into the atmosphere. One being our clouds. Okay, we have a couple different layers of atmosphere, but our clouds will scatter the radiation back up into the atmosphere. When it hits the ground, right, the ground itself can reflect a part of it back up into the atmosphere. So like what you see here is only 47% of that radiation actually makes it, to the Earth's surface and it's absorbed, right? So only 47% is actually absorbed by the Earth, all right? So the extent to which a particular surface can scatter energy is known as its albedo, okay? So the albedo is given the symbol A or alpha, okay? And so albedo is the total scattered power, which means the total power reflected divided by the total incident power, which means the total amount coming through the atmosphere. Okay. Again, it's a ratio, so it doesn't have any units. But think about it: if all of the power were to be scattered, I'm sorry, if none of the power was scattered, then you would have a black body, perfect black body. It's just absorbing everything. If none of it was absorbed, if everything was reflected, you'd end up having a total reflective surface, right? Again, kind of like a disco ball or something. Okay, but we're talking about Earth, and so Earth's albedo is 0.3. So that means that 0.3 or 30% of the power that comes to the Earth is reflected back out into the atmosphere. Okay, and that 0.3 doesn't necessarily mean that it's land. It could be land. It could be ocean. It could be ice caps. It could be desert. It just depends on where it is you're looking at. But the average is 0.3. Okay. So you should now be able to talk about greenhouse gases and using emissivity and albedo and the solar constant. In the next activity, we'll talk about the infrared radiation and what happens there, which infrared radiation is the radiation coming up from the Earth, and then be able to put that all together and look at it from the standpoint of what is this greenhouse effect that's going on. All right, go Hawks.